Hello? Hello?
Sir, good morning, sir.
Good morning. Good morning. Actually, I had another class just now. It's over. Okay.
Yeah,
No problem. Yeah, we can continue, start. I had my regular class between
Okay, sir.
10 to 11.
Now you can share your PPT, sir.
Yeah.
Sir, shall we start, sir?
Yeah, please go ahead. Please go ahead. It's already 5 minutes late. No problem.
Yes. So, good morning to all of you. So, today is the second day, first session by Professor K. Srinivas Reddy, sir. So, before handovering the session, I would like to introduce the Srinivas Reddy, sir. So, Dr. K. Srinivas Reddy, sir, obtained his PhD from Indian Institute of Technology, Delhi, in the area renewable energy in 1999. And then sir has joined at the National Institute of Technology, Warangal in June 1999. So after a brief service about 4 years at NIT Warangal, sir again joined at IIT Madras in April 2003 as assistant professor. So presently sir is a professor of mechanical engineering at IIT Madras and also a honorary professor at University of Exeter, UK. Sir also served as an adjunct professor at Central Electronics Engineering Research Institute CSIR Chennai in the year 2014 to 17. So Sir is a fellow of the National Academy of Engineering and and also specialist in renewable energy with a special research interest on concentrating solar power, energy efficiency and environment. And Sir has 8 patent applications and more than 280 publications, of which 150 papers in reputed international journals, including 5 review articles on solar energy systems and energy storage. So, Sir co-authored the book on sustainable energy and the environment, a clean technology approach. So, which is published by the Springer and book chapters on solar energy systems are more popular among energy and environment community. So, SAR is actively involved in the implementation of solar thermal technologies for power generation and process heat applications through design, development, demonstration, deployment using the 4D approach. So, SAR has executed several research projects related to solar energy and environment funded by the various national and international agencies like DST, MNRE, AICTE, RCUK, EPSRC, UKIERI, and IC Impact. The SAR work on estimation of thermal conductivity and thermal physical properties and characterization of engineering materials significantly benefited the industrial associates for development of energy efficient thermal insulation materials. So for this recognition of SAR work, SAR received several awards such as WSSET Innovation Award, Sri J.C. Bose Patent Award, and twice the Bhagyalakshmi and Krishna Iyengar Awards. Also, one career award for young teachers from AICTE in 2003. Very recently, sir received the Mid-Career Level Institute Research and Development Award in 2018. And also, sir is an expert committee member in various selection review committees and the visitors nominee for IIT Delhi. As a part of human resource development activities, Sir supervised over 176 UG, PG, and PhD students. Most of them are well placed and working now in prestigious organizations. So, Sir organized several national and international workshops on advanced renewable energy technologies. So, this is only short and brief bio sketch of Professor K. S. Reddy, sir. For complete details, the participants can log into homepage of iitmadras.ac.in oblique KS Reddy oblique. So you will get the complete details. So with this, so Sir is going to deliver an expert talk on solar energy technologies for industrial process heat and power generation. So this I request Professor K.S. Reddy sir. So please go ahead, sir. Over to you.
Okay, thank you very much. At the outset, I thank the organizers for inviting me. You can, I hope you can hear me well.
Yeah, sir.
Okay, and also you can see my presentation.
Yeah, yes, sir.
Okay, very good. So at the outset, I thank the organizers. I'll give a talk today, solar energy technologies for mainly industrial process heat and power generation, how we can use concentrating solar power for mainly process heat applications, because you know that in India, 2/3 of primary energy being used is in the form of heat, mainly in industrial processes, through fossil fuel combustion and so on. So therefore, it's important to come up with solar energy technologies for meeting the process heat requirements, and there is a wide ranges of process heat applications. And apart from that, how do we generate electricity by large scale power generation? That is complete high temperature power generation that we'll discuss here. So if you look at the solar thermal collectors, perhaps you have already attended, learned about solar energy before, but I'll give you a main glimpse of the conversion technologies. Mainly, the sun's energy is converted into heat in the form of heat by a collector, which we call solar thermal collector. And this collector converts solar energy into heat. And that heat, because you know that the solar energy is in the form of electromagnetic energy, and that is absorbed by solar collectors and then subsequently transferred into heat. And this heat, we can use it for some cycle, which is a heat engine. You know, most of your mechanical engineers, you know how to supply heat to the heat engine, and then you know that heat engine works under a cyclic process where at the boundary of the cycle is heat and work interaction, and it also requires a heat sink source and heat sink. Wherever the heat is added at the source at higher temperature, and heat is rejected at the sink at lower temperature. In the process, it produces work, and the work is coupled to the generator, and then generator produces electrical energy, whether it can be a grid connected mode or standalone mode. But the solar energy is in intermittent nature. It is available only during daytime. So therefore, we need to make it more reliable uh, by adding the storage. This could be some thermal energy storage, or we can also hybridize with other sources of energy, which is in the form of auxiliary energy. So it's a continuous conversion of solar into heat and subsequently to the mechanical and of course electrical energy. This is called power plants. And there are different types of power generating systems, which could be either mirror systems or non-mirror systems and air moving system. Broadly, the power so thermal power generation is classified into non-mirror systems, mirror systems, and air moving systems. And if you put them together, what are the different mirror and non-mirror systems are these, like solar pond, and I will explain you these details later. But solar pond is whose concentration ratio is 1, and it operates at 95 degrees Celsius, and whose power ratings are about 5 megawatts. And then flat plate collectors with 200 below 200 degrees Celsius and with less than 1 megawatt, and evacuated tubular collectors whose temperatures is in the order of 250 degrees Celsius. Power ranges are 1 megawatt. Whereas mirror systems are mainly four type of mirror systems have reached to the stage of maturity, and they are parabolic trough, which can be up to 100 megawatts, and temperature is for about close to 400 degrees Celsius. Central tower, whose temperature is 1500 degrees Celsius, and somewhere in the order of 200 megawatts can be produced. And parabolic dish is again 1500, and linear funnel reflector is same as parabolic trough. There are air moving systems where the working fluid is air, and it can mainly the concept of draft and draft, updraft, and wind turbine effect is considered in this, and this is called solar chimney. Then this downdraft is called snap system, snare aero electric power concept. If you look at the solar energy potential across India, you can see that there are a lot of areas where we have a high intensity solar radiation, where we can convert solar energy into electrical energy effectively, and where we have a lot of potential for solar energy. And there are, as you know, that in India about 250 to 300 clear days are available, and global radiation annually it's about 600 to 2200 kilowatt hours per meter square of area. So therefore, there's a lot of potential, and which can be equivalent to about 200,000 megawatts. About 4% of the Indian desert area is enough to come up with this, and we can also combine with coal and solar power plants. Why solar thermal is because it's easy and flexibility of integration with fossil fuels are easier, and large scale energy storage can make extended daily hours of operation possible, because when we want to make these solar energy systems 24 hours, we can still do it with energy storage. That is only possible through thermal energy storage. So the hello. I hope you can hear me. So solar thermal is about twice efficient as the photovoltaics, and cost is also less as to build. But nowadays, the if you look at on cost to cost basis, on energy generation based, it is better. And transition to the renewable via add-on existing power plants is also possible. We can integrate with coal-based power plants or gas-based power plants easily. So therefore, the solar thermal technologies, if we broadly put it into, because we now consider only mirror technology, which we call them as a CSP, concentrating solar power technologies, and they again broadly classified into medium and high temperature. If it is temperatures are between 100 to 400 degrees Celsius, then it's a medium temperature. The parabolic trough and linear reflectors are the technologies which can be employed for such operating temperatures. Whereas high temperature is a parabolic dish and central tower, the temperatures can go much beyond 400 degrees Celsius, and we can, as you know, that the heat engine efficiency increases with the source temperature. So therefore, if we supply heat at higher temperature, the efficiency of the heat engine is better. So that is what, higher the temperature, better the efficiency. Now, you have seen the conventional heat engine based power plants, mainly Rankine cycle based power plants. And this Rankine cycle based power plants are basically, it's a heat engine, and it operates between source and sink, and heat is supplied at higher temperature at the source. Generally, this heat is supplied by the fossil fuels like this coal. And when we burn coal, and it produces heat, and heat is again, you know very well, Rankine cycle operation. It operates both see the at a constant pressure heat addition, and isentropic expansion, heat rejection at constant pressure, and again isentropic compression, and it produces electricity. But if we replace this, because the sink temperature is not dependent on any other factors except the environment plays a major role in sink temperature. So whereas the source temperature depends on how we supply the heat, and this heat can be either fossil fuels, or if we replace this fossil fuel by the sun, then it is called concentrating solar power systems. And this sun can give the same amount of heat at the source. But how do we convert the solar energy into heat? There are four mature technologies, which we call them parabolic trough, parabolic dish, linear frontal reflector, and central tower. So these technologies is not only used for heat in for power generation, but also process heat. As I mentioned, that my talk is on also process heat, uh, applications also. So these are the four technologies which have reached to the maturity, and then they can give the required heat input with the appropriate energy storage technologies. So I will concentrate on these technologies, how they can be converted into useful heat. You can see that their concentrating technologies are in this. We can go even higher temperatures like solar furnace. So the based on the concentration ratio, they can be classified from lower concentrations like a compact linear frontal reflector to parabolic trough, central tower, and parabolic dish, and then furnace. This is the array of concentration, and the concentration ratios can be greater than 1000. That means we can concentrate the sun's energy into 1000 times, so that we'll get a very high temperatures. And we will discuss in detail how these how do they work, and so on. And as I mentioned that the power plant cycle or heat engine can be based on various cycles. Either it could be Rankine cycle using water or organic fluid as a working fluid, and Brayton cycle using helium and air as working fluids, hybrid combination of both Rankine and Brayton. Stirling cycle. Stirling is also another cycle you perhaps studied very well in that, and it's a regenerative cycle. And we can also use it mainly for modular sizes for power plants. So we can go for Stirling in cycle. And as I mentioned earlier, it could be low temperature, medium temperature, high temperature. The temperature of heat supply as source depends on the how do we supply the energy to the cycle. And if it is a low grade heat, then we can go for low temperature applications. But if we go for medium temperature and all, and as I mentioned that the efficiency, the concentration ratio versus the temperature for different cycles, here you can see at this Rankine cycle is somewhere used up to 500 concentration ratio, and the operating temperature can go maximum of 600 degrees Celsius. Whereas the Stirling engine is the next level. It can up to go more than 1000 concentration and 800 degrees, and Brayton cycle can go beyond up to 1500 degrees Celsius and then higher concentrations. The efficiency of the cycle is important, and if higher the cycle the temperature, higher the efficiency. But the problem with how do we generate this heat? We can generate a temperature very high temperatures, heat at a high temperatures, but obviously what happens is we can generate a very high temperature heat, but that is subjected to your the environmental condition. As we go for higher and higher temperatures, obviously it also loses heat to the atmosphere, because we cannot go for higher delta T's, because as we go for higher delta T's, the heat losses will also be higher. So therefore now we need to get this temperature by a solar collector. The solar collector collects solar energy into heat. As we go for higher temperatures from the collector, you see that if it is at lower temperature, the efficiencies are fairly better. But as you go higher temperatures up to 1400 degrees Celsius or so, then the efficiency drops substantially. Somewhere here you see that close to 45%. But whereas the engine efficiency, the cycle efficiency increases with the temperature, as you know that. And but the power plant, concentrating solar power plant, is a combination of the collector as well as the collector field as well as the engine. Then we have to combine these two. When we combine it, we'll get an optimum operating point. This is about close to somewhere 750, 780 degrees, where we get the efficiency of 35, 36%. So therefore, a solar power plant which operates at 7 to 800 degrees Celsius can give about 30 to 35% efficiency, depending upon the pressure parameters. So therefore, which is the same as the conventional coal-based power plants. So therefore, the solar power plant is as efficient as the coal-based power plants. Then we will look at how these different technologies are. The compact linear Fresnel reflector is the rest of the part is same. The turbine side is the same. This is the turbine part, and then this is a generator, and then it goes to the grid. But this heat steam generation is very important. The steam generation is, there are linear reflectors, mirrors, and the sun's energy is reflected back to the reflected to the receiver here, which is placed about a higher altitude, about a few meters above the ground, and the radiation comes here and gets reflected here. And when you send the working fluid through this, and it will become steam, and then it expands onto the turbine here. So this is a simple technology, and here this is the main solar collector field, which we call compact linear frontal reflector. So why compact? Because they are very closely spaced. So therefore, there is a less area ground, because you know that in solar power plants, the ground area is very important, land area is important. We need to minimize the land area as much as we can, so that we'll have a better yield. The another technology is parabolic trough power plant. Actually, you know that yeah, because we need to concentrate solar energy by a solar collector. The important concentration technique is you come up with a parabolic mirror, so that the radiation focus onto the uh, receiver or focus. Here all the rays goes to this focus. But then this mirror needs to be made such a way that it's a parabolic shape, so every ray goes into the this to the receiver. And then if you extend linearly like this, cylindrically, then it's called cylindrical parabolic concentrator. Here you have this here. So such collectors are connected in series and parallel, and again to produce the heat, and that heat can be used to heat is in the form of steam or a hot fluid. This can be taken here and then supplied in superheater, reheaters. This is a superheater here, and evaporators like a boiler and then economizer, and it goes back here like this. So it comes here. But if you go for two-stage power generation, then there is a reheater here. And but some extra energy can also be stored into these tanks, where this can be even recirculated back whenever it's not required. So this is a power plant, parabolic power plant with thermal energy storage. So when you have excess energy here, it's stored here in the form of extra energy, and then that can be this. You have, when extra energy is produced, you can keep it in storage, and whenever it is needed, you can shift it to the after sunshine hours, because this is the capacity of the plant, and you can use it from directly sun. This entire area is directly sun, but the extra energy is beyond the sunshine hours. But if you want to increase this capacity can go up to 16 hours or even more, so that we can make it 24 hours of operation. So that depends on the how storage, or otherwise we can go for like a hybrid system, like fossil. Either you can go for fossil fuel or biomass or hydrogen storage, any one of those. A typical parabolic trough collector looks like this. You can see the mirror is made of parabola, uh, and then all the reflected radiation is focused onto this receiver. And if you send working fluid, cold fluid one end, and you'll get the hot fluid the other end. So here it consists of an absorber tube and reflector, and then solar field piping plus support structure, because it needs to be tracked continuously from along the sun here. So it has so that all the radiation will be falling on this receiver. And if you put them in series and parallel, you can see this is such a massive power plant here, which is located in California, about 554 megawatts. And in India also, you can see such power plant in 2-3 regions, and mainly the closest one for your I think for your location is Anantapur. Anantapur Mega Engineering company called Mega Engineering, they have developed a parabolic trough collector plant close to Anantapur, which is made similar to this line. It's a 50 megawatt power plant. It produces electricity. Those who are already seen, it's okay. If you have not seen, you can go and see. It's a massive power plant. And you can see that these two receiver tubes, and then mirrors, and then tracking system, and it goes almost 600 to 700 acres of land in Anantapur. I had visited once twice there, and you can see those who are interested to visit. And then at the center there is a power block located, and all around is the mirrors. And this is based on, you see this is a cooling tower, and there are two energy storage tanks here, to which can keep the energy storage for the beyond sunshine hours. And this is a complete power block, and it's a Rankine cycle based power plant. So you can see such plant. And the next technology is the solar central power tower, where because the higher concentration can be attained by central power tower by using heliostats, and the heliostats focus on the tower. And but the temperatures are very high, as I mentioned earlier also. It may go to 1500 to 2000 degrees Celsius, 1500 to 2000 degrees Celsius. Uh, but what happens is at such uh, high temperatures, high temperatures, you cannot use water as a working fluid there, because there is a possibility of dissociation of water. So in order to avoid that and take care of the cycle temperature, generally we go for this molten salt. This is a molten salt. Molten salt is circulated this, and then they stored in both cold and hot storage tanks. Here you see this is hot storage salt tank, and then from this the salt is circulated in a heat exchanger, molten salt, and then the other side is the Rankine cycle here. The salt, high temperature salt will give the heat to the water, and the water becomes steam, and then superheated steam is generated in this evaporator, and then comes to the turbine cycle, and then it expands in a turbine and then connected. This is the Rankine cycle, and of course we need to reject the heat here by cooling tower. And this is the, so the advantage with this is it can operate in this two loops. One for primary loop is a salt loop, and secondary loop is the steam loop. And the salt can be stored in big tanks so that we can extend the operations beyond the sunshine hours. I have seen a plant in Spain based on this. It works 24 hours, about 16 to 20 hours of energy storage, and it's a continuously operated. So such plants are there. You can see this here. There are mirrors placed here. This is again California, but I have visited Spain. Used to be one of the dominant concentrating power technologies. I have visited one or two plants where in Sevilla, there is a location called Sevilla. These plants are located. You see that this concentrated solar radiation is focused onto the receiver here at bright sun, and then molten salt is circulated here and bring. See, sometimes if we want to use other than the molten salts, we can use still air. Then we can drive the gas turbine cycle based on this. So either air or molten salt can be used, but water may not be appropriate because for this high temperatures. And these are the two storage tanks. We can use them alternatively based on the requirement. And if you look at it's a bird's eye view, it is like this, and such several plants can be. The center location you have a power plant, and the mirrors are surrounded by these. And in fact, one of my students also has done ray tracing for this. See, you can see there are mirrors missing here and there, because based on the ray tracing where to be installed, what mirrors, and how, then what is the field study and all this. We also published a paper on how to come up with a heliostat array for optimal concentration of the flux on the receiver, central receiver. And this is the in Germany. We can see that a massive solar concentrator. As you know that by using solar concentrator, we can raise the temperature up to the surface temperature, theoretically up to the surface temperature of the sun. So that means surface temperature of the sun is somewhere 5,000 degrees Celsius. So mean to say that we can even raise, even if 50% of that temperature will become somewhere close to 2000 to 3,000 degrees Celsius, which can make these metals also melted. So this is the furnace. A big building is used as a concentrator, and then it focus the radiation from the, this is in Spain, sorry, in Germany. The radiation will sun, if sun is here, uh, the radiation is reflected back to this receiver here. So this is the place where the furnace is located here, and you can see that this is also almost 4 to 5 or more than that 6-story building here, and in this the furnace is placed. So the reflected, because this is very massive structure, because if you cannot keep it in outdoor condition, because you have a wind loads and other things, so the building itself is used as a support structure. So this is what. Then the parabolic dish collector system, because it's a 3-dimensional parabola, and it involves various components that includes concentrators. That concentrator means a single facet concentrator or multi-facet mirrors, or single stretched membrane concentrator, and it also requires tracking system, whether we go for continuous tracking or discontinuous tracking, or azimuth elevation tracking or polar tracking. Then we need engines, receivers. That receivers could be solar Stirling receivers, or direct illumination receivers, or indirect illumination receivers, Brighton receivers. If air is used, then it's a Brighton receivers. Then engines could be Stirling cycle or Brayton cycle, depending upon the working fluids, or even Rankine cycle. A typical concentrating dish collectors looks like this. Is a based on stretched membrane. I will give also our technologies later, dish technologies. These are stretched membrane based collectors, because it's very difficult to make parabolic shape by a fragile mirror. So therefore, we need to make them more accurate, so that the radiation reflects onto the engine here, Stirling engine. It can be a discontinuous structure. If it is a discontinuous, like these facets are there, and all the facets are made into a globally parabolic, and that reflects here onto the receiver, which is called Stirling receiver engine. This is a multifaceted, and this is a stretched membrane system. Stretched membrane means the mirror reflectors are stretched into to form a parabolic concentrator. It's about 10 kilowatt. It's a old system which is being implemented there. And this is another dish collector which is in Australia, ANU, Australian National University. It's about 400 square meters area. This is, I think, perhaps the world's biggest dish collector. Then it requires a monotube, because it's completely covered with 54 mirror panels, and then it is tracked by an hydraulic structure here, hydraulic actuator, and then the concentrated radiation is focused onto this, and then this monotube boiler produces. It's a single monotube, means it's a one screw boiler, and this one screw boiler will get a superheated steam, and that steam is expanded in a turbine, either turbine or the engine, steam engine. So this is such a system here. It's a 4-cylinder steam engine is used to drive the motive power. So this is such a difficult. And the other one is parabolic trough. But we need to do extensive analysis of these solar concentrating power plants. As a part of our activity, we have done extensive analysis on 4E analysis: energy, exergy, environment, and economic analysis of line focusing collectors. Either it could be parabolic trough or linear funnel, and these are the some specifications based on the length and sizes, and their cost comparisons are also given here. And based on that, we find out the levelized cost of electricity tariff, and so that whether the power generation is viable or unviable or conditionally viable, depending upon the conditions. So if you look at the power block, the power block consists of this. It's you have a solar field here, and that field produces heat, and that heat is expanded. The steam is expanded in a turbine, and you'll have a deaerator, feed water heaters, and of course condenser. And based on that, we have considered the atmospheric condition as Indian condition, like that 1 bar and 33 degrees Celsius, and condenser pressure is about 10 kilopascal, and condenser cooling water temperature is considered as 10 degrees Celsius, but of course that differs from location to location and also from season to season, whether summer to winter and so on. So it is considered as a 30 megawatt power plant with whatever is there in Spain that is adapted here with the 215 megawatt turbines, and temperature and pressures are correspond to 55 bar and 270 degrees Celsius. And we have done a comprehensive energy exergy analysis. You know the energy analysis. Energy analysis is based on first law analysis, the quantities of this, and whereas exergy analysis is based on the quality of analysis and mainly considering irreversibilities into the account. And these are the equations. I'm not going in detail, and these equations can be used to estimate the both energy and exergy, and so that we can find out where the exergy distraction or irreversibilities involved, so that we can minimize the irreversibility. Subsequently, we can improve the performance of the plant. And based on that, 5 megawatt standalone power plant has been considered, both parabolic trough and linear funnel, because this LFR is the linear funnel. There is a difference between the collector field here. Both have been analyzed with different steam parameters at different conditions, but the cycle remains same. Both the cycles are same. And then we have come up with the energy and exergy flow diagram for this, and energy flow diagrams and exergy flow diagrams for LFR is there. If you look at the energies, the net output is about 11.69%, but the major losses is in the condensers, and by the receiver, followed by the receiver, and followed by the concentrator losses when we do it first law analysis. But when we go for second law analysis, it will be different. So in second law analysis, the mainly concentrator has the highest heat losses, about 55.48%, and net output is better in this case. But you can see that the receiver analysis, receiver losses are almost 50% against the first law. So that is what we can see, that we assume that here the concentrated losses are minimal in case of first law analysis, but actual case, if in terms of quality of energy is concerned, it is a major here. So therefore 55 means almost more than 50% of the energy is being lost in concentrated losses. So therefore one should focus here on this area, how to reduce that. Similarly, if you can do the first law for PTC, whether you go for LFR or PTC, it looks a similar pattern, but again the concentrated losses are substantial in this case. But the parabolic trough is better as compared to this because of the less irreversibility. There is only 45% against 55%. And then your output is increased by 23.64%, slightly higher. So therefore, if you do based on energy and exergy analysis, PTC appears to be better than the LFR. But we can also integrate this with the coal-based power plants by adding collectors into the feed water heater line. This is a typical coal-based power plant. You can see with the solar collector here. The coal is fed from the bunkers here, and then there's a pulverization of this, and it's burnt here in a boiler, and this steam, superheated steam, is expanded in the turbine and then condensed here. And before, after condensation, before it enters into the boiler back, then you can introduce the solar collector here. So this will be additional values in twofold. One is either we can increase the capacity of the plant, or we can reduce the coal consumption. And once it's coal burned, and you go for air preheaters and then ESPs and goes on. This is the typical. And as such, a power plant is developed in Queensland in Australia. You can see that this is a coal-based power plant integrated with solar field here. This is the solar field, LFR field, which is connected to that, and so that the coal consumption is reduced some extent, and we can also operate at higher loads by adding extra during daytime. There are other thermal chemical energy storage by solar dishes. We can use this is Australian National University college. We can dissociate ammonia into nitrogen and hydrogen, and then through the heat pipe technology, we can use it in the night time so that the exothermic endothermic. See, in ammonia can be split by adding some heat, and it becomes nitrogen and hydrogen. And when you combine these, uh, these two, uh, then you will get back the same amount of heat. Same amount of heat. So during daytime you can split this, uh, break it, and during night time you combine it so that we can use it as an energy storage system. So then, if you look at the renewable energy technologies, mainly I'm looking at the process heat side. So far, I have discussed power generation, but if you look at the process heat, the solar energy can be directly converted, indirectly converted into water, wind, hydropower, wind, biomass, and ocean. But direct conversion is this. Solar energy can directly convert it into photovoltaics, but I'm not going to discuss this. But the other process, converting solar energy into thermal through various process heat applications like hot water, drying of food, cooking, distillation, refrigeration, greenhouses, and power generation. So far, I have discussed how the power can be generated by the concentrating solar power technologies. You have seen that. Now we will also discuss some of these factors here. I have mentioned in the first slide that how to convert solar energy into thermal and subsequently power and then electricity. But apart from that, you can also have photovoltaics conversion to electricity. But this can be used for with energy storage here. This storage plays a major role. Now, if you look at two tank storage here in parabolic trough collector, the thermal energy storage plays a major role. And these whenever the extra energy is there, that can be used in to store in hot tanks, and whenever we need it, then we can circulate it and get the back here. But the because when we are talking about energy storage, as I mentioned, that the storage is for, see, the solar energy is available only for 8 hours in a day, but remaining 16 hours, if you want to make it 24 hours, remaining 16 hours is the storage. So this is 16 hours storage means that we are almost storing two-thirds of the actual energy being produced during the daytime. So therefore, then we have to make the solar field almost 3 to 4 times bigger. So in order to make two times the energy storage, but again, the field will be much bigger. And apart from that, the energy storage tanks will be very big because we are almost operating double the time the actual operations. So therefore, the fluid tanks are massive. And when having such a massive tanks, two tanks means it becomes very expensive. But one way the collector field the higher side, and then tank is also high. So therefore, we have made an attempt to come up with a single tank, which we call thermocline tank, and so that the two tanks are replaced by a single tank, so that we'll have a better performance as well as the cost considerations. So then this has been analyzed in a holistic way for how to store energy in a different way with different considerations, mainly stability of thermal stratification and large buoyancy forces, how they are flying, and high energy volume densities, and then how the single tank can play a major role in terms of this. One of my students has done with the different energy storage materials like organic metals, inorganic eutectics, and so on, and depending upon the operating temperatures and operating conditions. And this is the tank, direct packed bed tank. Thermocline tank is considered here for large scale operations, and with the complete distribution, both charging and discharging conditions. Charging, it behaves differently, discharging, it behaves differently. Based on that, we have completely analyzed this and come up with, and you can see the papers we have published, and on my web page you can see them if you want to know more about this energy storage with power generation. I will discuss some of the process heat plants which we have developed as a part of our um, technology development, and we have developed more than 20-25 technologies, and I have listed here top 10, 20 technologies, which is based on the 4D approach: design, development, demonstration, and deployment approach, and have listed here. But I will go through these so that those some of you are attending my lecture first time, you can take up and then you can use it for how the process heat applications can be utilized based on the concentrated technology. These are the concentrated technologies which we developed at IIT Madras. This is a parabolic dish, this is a square dish, and this is a circular dish. And these are my group, my students. And if you look at these on for the approach, design, development, demonstration, and deployment approach, this is a parabolic dish collector, which is a point focus collector. The solar radiation is concentrated onto the receiver here, and it consists of the receiver here and the reflector here, and then this support structure here, and it is tracked continuously to get the solar radiation. This is a monotube boiler, and the water, cold water enters here, and then hot water comes from the other side, and we can use it for. And the capacity of this is about 20 square meters, and which produces 15 kilowatt thermal energy, and it's at 640 degrees Celsius with a 67% efficiency. The another one is a PV with a tracking system, because we are being a mechanical engineers, we have very limited role to play as far as the photovoltaics are concerned. But at the system level, definitely we can have a role, because we can improve the system performance by adopting appropriate tracking technologies. And we also worked on desalination, because potable water is very important, and most of the Indian water bodies are polluted, so we need to have potable water, and especially the coastal areas like Chennai and other locations, because the water is scarce. And then we can convert seawater into the potable water by appropriate solar technologies. The other one is uh, this integrated collector storage system, and solar trough collector, which I have already discussed. This we developed at IIT Madras, which is about 15 square meters and 8 kilowatt thermal energy at 350 degrees Celsius with 62% efficiency. And this is a concentrating photovoltaic. As I mentioned, that we have less role to play in photovoltaics, but we can do at system level by appropriate cogeneration and polygeneration concepts. So as a part of that, we have developed a concentrating photovoltaic system where the concentration of energy can be used to illuminate the photovoltaics, mainly high triple junction photovoltaics, and in which the power output is much higher. And apart from that, it also produces the heat in the form of cogeneration aspect. We have done a large scale configuration mainly for process heat application as well as power generation, and which because when we go for more number of collectors, they need to be placed one after the other, and then so the collector field is very important. The field design, because single collector design is altogether different, and it's a different ball game when you go for a field, because we need to look at the space, the land area, ground utilization, how much is what fraction of ground that can be utilized with mirrors, and how do we optimize this with respect to the sun's motion, and whether because when they are closely packed and we have the sun moves from north to south. Hello, hello, can you hear
Sir.
me? Can you hear me?
Yeah, sir.
Okay. There's no problem. I saw a message that your internet is unstable. So, but I think you can hear me well, is it?
Yeah, yes, sir.
Okay. Thank you. So then we can look at the field, how we can put it in northwest, northeast, and sorry, east and west direction as well as south north direction. Based on that, we have come up with a east-west direction non-dimensional collector field configuration and north-south non-dimensional collector field configuration. If one collector is surrounded by several eight of such similar collectors, how this will cast a shadow on other adjacent to that, depending upon the time and also depending upon the location. So we have done comprehensive analysis for India, complete India, from this Kanyakumari to Jammu Kashmir, Ladakh region. Recently, we also proposed one energy storage for Ladakh region, where we can store energy and for process heat applications. So if you integrate this with a power plant and then use it for power generation across India, and based on this technology, based on the current technology, how we can make it viable or unviable or conditionally viable, where the green color locations are viable with this present technology, blue are conditionally viable, because here we have calculated the levelized cost of electricity, land utilization factor, and you see this LUF is a land utilization factor. How do we operate, at what time it should be operated, whether the sunrise time plus 5.5 hours or sunrise time plus 2.5 hours, what is the minimum distance, then accordingly we can optimize the operating conditions also, and then found the levelized cost of LCOE, levelized cost of electricity, land use factor, and energy generation. All these are calculated and come up with a holistic approach of viability and conditional viability and non-viability. This is another technologies, parabolic dish with the multifaceted. You can see the difference between these two. These are multifaceted systems, and this is in fact, we have been working on dish technology last 20-25 years, and this is the sixth generation, fifth generation dishes, because a lot of improvements have been incorporated in terms of materials, in terms of performance, in terms of components, in terms of efficient tracking systems and so on, and therefore there was a continuous development, and it is connected to a air conditioning system at the backside. You see, this is a vapor absorption air conditioning system at the backside. And this square dishes, which are we are used for, we have used for concentrating photovoltaics. We developed the concentrating photovoltaic modules. That's called CPV modules. Concentrating photovoltaic is a CPV cell modules with appropriate heat exchangers, and then the cells are connected in series, and this triple junction. You can see that this is about 30 centimeter by 30 centimeter, which can produce about close to 3 kilowatt system. That means in a normal surface, it's about close to 20-25 square meter area is packed into a small 30 centimeter by 30 centimeter. But the expensive solar PV material is replaced with inexpensive glass mirrors, so that we can have a better overall conversion efficiencies. These are the heat exchanger designs with the heat recovery system, with the different PV configurations and so on. And parabolic trough I have already mentioned, because large scale power generation, mainly for process heat application, we need to do a holistic analysis, including optical analysis here. Optics is a major important. It is through ray tracing technique. The solar ray is how it is reflected onto the receiver with the deviation, because we need to know the surface characteristics of this mirror, and how, if there is any deviation in the surface, how this is reflected onto the receiver and how it is dispersed. Because the higher the dispersion, then your image of the receiver is different. Then this is a comprehensive approach with the ray tracing technique, and based on Monte Carlo ray tracing technique. And apart from that, the receivers need to be analyzed for thermal instability and two-phase case, because two-phase problem is a major issue in receiver. We have addressed by going for porous receivers and with different receiver conditions, and based on that, we have come up with an appropriate technology. Here, And you can see that it has been evaluated for different working fluids like water, terminal oil, and for different conditions. And then the performance is seems to be better. And we also estimated the overall heat transfer coefficient based on the various this we can see in these papers, the details. And based on that, because as I mentioned that we have seen that in Anantapur large scale power plant, mainly Parabolic trough. See here, this is that such a parabolic trough collector. This almost 5.77 meters aperture here. This is about 5.77 meters. This is the international standard collector meters aperture, and we can go length like this. But this we have tested one receiver which is about 4 meters size, and we developed a tracking system, and then complete balance of plant here. This is a balance. This is used for power generation, but when you this is meant for power here, but the process heat is by this small collector here. This is also parabolic collector, but it is half of this. It's only 2.5 meters aperture, and then length is about 12 meters, and this is connected to a balancer plant with the heat exchangers for both direct steam generation as well as the this is for direct steam generation. This is for terminal fluid. So therefore, for direct steam generation, the heat exchanger is a vertical type of heat exchanger, whereas thermic fluid based is a horizontal heat exchanger here. So here oil is in this case oil is circulated, whereas here the water is circulated. So that is the difference here. This is for process heat, and it's placed on the rooftop, fourth story. There is our classroom complex in IIT Madras. It's a on fourth story building, and it's on the top of the floor because it's very challenging. We cannot. It's a heavy structure. We cannot put it onto the roof. So therefore, we have made separate foundation for this in order to isolate the roof from the foundation, so that there will be less load onto the roof, and the entire load will go to the columns. We have seen based on that a parabolic trough collector is an accurate version, but if you go for inaccurate version, it's a linear funnel reflector. These are flat mirrors. If you see that these are massive, bigger one, but if you look at these are small mirrors which is close to the ground. If you can see a person is standing, people are standing here, how big these are. Whereas the mirrors which are close to the ground, you can see people are standing here, and it is very close to the ground. So therefore, there is a less wind loads, and it's very closely packed. So therefore, the land area utilization is different, but the efficiency will be different as compared to that. These mirrors. These mirrors reflect solar radiation from here to this here, and then the water is circulated from here, and then it goes into the energy storage here, and then there's a steam drum here, and then to the cycle, and then there's a separation of this. Then the dry steam will go to another collector and becomes a superheated collector, superheated steam the other side. So this is the way in which it works, and we have installed this in a school which is called Patashala in Vallipuram, close to Kanchipuram district. Is about 80 kilometers from the from IIT. And this is LFR collector with a 50 kilowatt thermal. We have now going for 500 kilowatt system, which 350 to 400 degrees Celsius at 50 bar pressure, and it can be a cogeneration, trigeneration system, and it can produce electricity, hot water, cooking applications, as well as the air conditioning. We have done a lot of extensive uh, analysis on receivers, mainly how to put the receiver here and do it in indoor testing, and then not only for heat transfer point of this is heat transfer concept, this is a flux distribution concept. We have made a lot of simulations on indoor conditions, because in real time it's very difficult to do the test on receivers. So therefore we have to do it in a simulated condition. These lamps are used to simulate the solar energy and then used for this purpose. And some of our technologies have been transferred to the industries. these parabolic dish collectors and trough collectors, and they have installed in their these are their brochures, and they have commercialized our technologies, and they are implemented across India. There's another hot water system for process heat applications. You know that the uh, s- uh, uh, the flat plate collectors, solar hot water systems. In solar hot water system, there are two components. One is the flat plate collector, and the other one is a storage system. But if you connect them, generally these in hot water system, we store the energy during the daytime and collect. We can collect and store it in a hot water tank, and then we use next day morning for our bathing purpose and other utilities, mainly domestic applications. But when the energy is stored in tanks, and then they are connected by grid of pipes and so on, and there are major source of heat losses, and storage is contributing about 60 to 70% of the total cost of the system. For example, for 100 liter hot water system with 60 degrees per day, 100 liters per day with 60 degrees Celsius. The cost of the storage tank is almost somewhere 60% or so, but whereas the collector is only 40%. The energy storage is a major component. So if we store energy in a large tanks, and then they also become the source of heat losses. So therefore we should minimize the heat losses from the storage. So we developed as a part of that the integrated collector storage system. That means the uh, collection and storage is in the same unit. This it collects here and also stores in this, so that there is no separate storage tank. But this top cover is covered with a honeycomb structure, and it looks like this. Here you can see that, and the cross section of this is this, and it is a very effective as compared to the flat plate hot water systems, and the cost of this is much lower than the flat plate collector. So its replacement is the this is a replacement for solar hot water systems. As I mentioned that this my one of my students worked on tracking system for photovoltaic panels. One of the undergraduate students, and he has developed a low cost passive uh, system for tracking, because it doesn't require much energy. Parasitic power is very low. So, but we get additionally about 20% in morning and afternoons extra. So this extra energy can be used with a passive without much additional energy. There is a counterweights which is very simple in that. Then the concentrating PV with line focusing, this radiation comes from the sun is reflected onto the receiver here. Then solar cells are placed in this, and at the back side of the solar cell, the water is circulated, and then it comes back here like this, so that the solar cells are cooled, and then the higher output can be attained. Then we have refractive type lenses, where the uh, lens concentrates radiation. This solar radiation comes like this here, and refracts, comes and goes into the point where you have a spot where the solar cell is placed here. The solar cell, and it's a triple junction solar cell. You can see here, and but there is a secondary reflector placed here in order to make uniform flux distribution. And this is another hyperbolic concentrator, which is used for parabolic process heat applications here. This process heat applications you are seeing here, and this is a passive collector which doesn't require any tracking, and it captures maximum amount of radiation throughout the day. And again, optical analysis is very important, and then receiver analysis, because it's the heat transfer elements are very important, how to design them, and what is the minimum friction factor, and how to get the output, and then how do we integrate with the multi-effect solar desalination system. So then this is a desalination system which is integrated with the collector, flat plate collectors and stored here, and this evaporation condensation takes place here. You can see these papers and desalination. This is a optimal configuration to come up with the evaporation condensation in the same unit, and then you will get the overall output is better, and it can vary with the different stages, and with the yield is about 15 to 25 liters per day per meter square area with 40 to 60% efficiency. And it can also handle any type of water like fresh water, brackish water, or saline water or brine, because it can also be used for waste water treatment. Like we have developed technology for textile industries also. These are another vertical type of steels. One of my PhD students worked on that, and then it is vertical. So therefore, this surface can be used for both evaporation and condensation, and its yield is much better, about 20 to 25 kilo kgs per day. And the yield is better because of the large surface area, and also involves evaporation condensation is in an effective way. The another still is mainly for wastewater treatment. Wastewater is important. Here the brine or the wastewater can be treated in a stepped basin, and some water can be held in different stages, so that it's a cascaded mode, cascaded system with different steps. So therefore, the overall yield and energy and exergy yields are better, and the quality of energy, how we can utilize, can also be found by this, and the whose thermal efficiency is in the order of 45%. And the another concept is the solar process heat is a solar dryer, but it's used for waste, human waste treatment into fertilizer, converting it fertilizer. We have used a synthetic waste to convert we used a solar dryer for converting it, and mainly under clean and green toilets with a zero discharge toilet, zero liquid discharge, zero solid discharge toilets. And this is a part of our Indo-German Center for Sustainability has given this project, and we have done as a part of that. This is another effluent treatment plant, mainly so again process heat, because my entire lecture is on process heat and power generation. So therefore, the process heat is you use the process heat which is produced by solar collector, can drive off the effluents, and then convert these effluents into useful products and bring it back a cleaner water, so that we can recirculate the water. So this is such a system here. It's installed in Tirupur, Tamil Nadu, where it's a big, massive textile hub, and where the effluents are rejected into the open environment, polluting the agricultural fields and so on. So we install this in a textile industry. This Tamil Nadu Planning Commission has given this project to set up this, and this is a new technology, it's evaporative wind-assisted evaporative cooling system, where solar energy and wind are combined and then used for evaporating the wind and recovering some salts also from this, because dye a lot of salts are added, and those salts can be recovered, otherwise it will go into the environment. And we have developed this zero discharge toilet. Uh, the zero discharge toilet is both. We have used all types of solar configurations, including process heat concept. Then, of course, the pumps and motors are driven by the PV panels here. You can see, but this is essentially a desalination. This is a desalination unit, and there is a here you can see that there is a this is a desalination unit, and this is the drying unit, and this is installed in a hostel, Krishna hostel, in one of our hostels, and the solid and liquid separated and then conveyed to the top by a conveyor mechanism, and it's completely hermetically sealed. And then the liquid is separated here at the bottom, and liquid is fed to the desalination unit, and then solid is to the dryer here, and the dry material is processed and then brought back down here, either going for fertilizer, or you can burn it and use it for preheating of the water. And the water is evaporated and condensed and is used as a makeup water in this. And then the dryness, whatever the thick sludge is again when sent back to the dryer, and that is treated here and disinfected. And then this is complete, entire system is hermetically sealed. There is no human intervention. Everything is through conveyors and so on. So this technology we have licensed to one Bombay-based company. They are planning to commercialize. We are also working on the auto mobility. Here, this is only, this doesn't come under process heat application, but I want to just show how the mobility can be integrated with solar and battery storage. And this is compared with conventional conventional autos. And then we have done extensive economic analysis. One of my MS students worked on this, and he has come up with an extensive economic analysis and viability analysis, and it proved that based on economic analysis, this solar powered auto looks to be attractive as compared to this when we do both energy, exergy, and environmental analysis. And the another concept is producing electricity by biomass. Is a biomass solar integration here, and this is a biogas. This project is an Indo-UK project which we installed in Vishwabharati University, close to Shantiniketan. And the biogas is converted into electricity through this engine, and some part is stored. And there's a CPV system also here. You can see this is a CPV, because whatever we have done that work, it's CPV is electricity come process heat application. Both can be integrated here and supplied to the electricity here in rural application. These are the panels which takes care of the power, and it's mainly the integration system is very important. This is integrated with both grid as well as this is a grid as well as PV as well as uh, this biomass energy. All of them are connected here, and it's a complete integrated renewable IRES. Through we have developed a algorithm which is called ICCM, integration, control, communication, and metering concept. With this, we can control and communicate and meter it an integrated renewable energy system, and so that we can make it a standalone mainly for rural applications. So this is the last slide which I'm going to give. This is a characterization of energy storage materials and energy materials, because we need to develop the materials for low cost energy materials. So we need to characterize this material in terms of thermophysical properties. We developed a first of its kind and most accurate test facility for thermal conductivity for mainly industrial insulations, building materials, and energy storage materials, because this is based on one-dimensional heat conduction. So one-dimensional heat conduction, it's a steady flow system, and it's a steady state guarded hot plate system, and it's a very accurate absolute measurement system. And most of the industries who manufacture insulation, building materials, they come to us for testing of their materials, and we characterize the materials. So if you want more details, the papers are available here. With this, I conclude my talk. That I think resilient energy system is very important for with energy storage system, not but also integration of various energy sources. Not only single energy system can be enough. So we are coming up with an integrated future electric system which combines all these. Not only that, we have data science, and then data mining and communication, and ICCM, integration, control, communication, and metering are very important. So therefore, an important to have a most resilient energy generation and storage solutions for flexible and efficient system integration. Thank you so much. If you have any questions, please feel free to ask. Thank you.
So, dear participants, please unmute yourself and you can interact with Professor Srinivas Reddy sir.
If you have any questions, please feel free to ask, or you can put it in the chat box also. Uh,
Dear participants, if you have any questions, please.
I think if there is no questions, I thank the organizers as well as the participants for patient listening. Okay.
So thank you, sir, on behalf of Mechanical Engineering Department, and from my side, I am very much thankful to you, sir. So upon our request, you have given your consent to deliver a lecture on this faculty development program, sir. So you have introduced different types of solar energy systems to our participants, so they might understood what type of research they can do with solar energy. So this might be a very useful session for our participants. So thank you, sir, once again for giving your valuable time for us.
Thank you.
Thank you,
Thank
sir.
you. All the
Thank you,
best.
sir.
Thank you. All the best for the rest of the sessions.
Sir, we have the details about the previous. Can we send the same to you, sir?
Yeah, yeah. No, no problem.
Okay, sir.
Okay.
If possible, please send your PPT, sir, at least a PDF format.
Okay, I will do that. There is no problem. I will do it.
Okay, sir. Thank you, sir.
Thank you. Bye. See you.
Huh?
Sir, it is possible to get the PDF copy of Sir PPT?
Yeah, that's why I asked the Professor Srinivas Reddy, sir, to send it.
Thank you, sir.
So that this is the today's morning session, and today the afternoon session is by Professor V. Sivareddy, Professor of Mechanical Engineering. He is going to deliver a talk on renewable energy technologies for sustainable development in the afternoon session. So all of you, please join at 2 o'clock. Thank you. So already posted the feedback link. All of you fill that one.